Okay, today we will start talking about the functions, mathematics. Okay, but once again, my emphasis is I will talk about the functions from robotics point of view. Okay, here we go. All right, the functions. So I'm going to start talking about functions. No, before that, there's one thing I have to do. That is the constants and variables and the terminologies and as such. I guess you're familiar with those, but let me clarify some of those. General variables, we use x, y, z, u, v, w, etc., etc. And general functions, we normally use f, g, h. Those three, others as well, but positions, x, y, z is the typical one we use. And for the time, t and tau, this one here, oops, sorry. Okay, oops, I went too far back. Okay, this one here is a Greek character, tau, which corresponds to t in English alphabet. And t0 and subscript here, we have T1, T2, T3, Tf for the final, etc., etc. And for angle, we have theta, theta. There are two different ways of pronouncing it, but anyway, theta is the one we use quite often. And if you need more than one angle, we can use psi or phi or those characters. And angular speed, that's omega. Omega is exclusively used for angular speed. And torque is tau. So you say, what's happening here? We have used tau there as time as well. Well, unfortunately, we use tau for both torque and time. But fortunately, it is very easy to distinguish them according to the context. So there's no ambiguities there. Constants. A, B, C, lower characters and upper characters, and alpha, beta, gamma, those are Greek characters, etc. And index, the difference between index and the constants are real numbers, something like 2.5, pi, etc. But index, these indexes are integers, 1, 2, 3, 4, 0, minus 1, minus 2. I, j, k, l, m, n, those are the like ones. Either lower character or upper character. Okay, so that's the type of how should I say, variables and constants we use. Okay, so that's done. So we are now ready to start talking about functions. Okay. So functions. What do you imagine when you hear the word function? Since you guys are digital age people, so probably you can guess or you will imagine, you will find this image of tables. Well, that's what the computer does. But for human beings, graph is much more easier, much more understandable. And finally, functions can be given by an equation here. Theta of x here is given by this polynomial, and this equal here is what makes this equation. So which one do you like? Any one of them is okay. What is your favorite? Here in this course, because this is half mathematics, half robotics class, we use three equations with two graphs as well. Equations for theory, graphs for human eyes. Okay, basic functions robots. There are many different functions, but from robotics point of view, there are two major functions. One of them is the functions of joint angles. We already saw this, but in the two-link manipulator. Well, what it amounts to is thing called the kinematics. And from, well, ineffective positions. So what it amounts to is from theta to x, y. You know the joint angles, and you use that to compute the position of the end effector. That's kinematics. And then functions of time, since the robot does move, trajectories are described by functions of time. So those are sines and cosines here and time functions. Those are two major functions we use. And for actual form of the functions, we use those tools. I call that tools. Polynomials, you know this already. Okay? And trigonometric, wow. Can you pronounce this? Trigonometric? That's too much. So I will get rid of this and I'll just call trig. Okay. Sines and cosines. All right. The next one is exponential, e to the some power. Have you seen this in high school? If not, you're lucky because you will learn from me. That is going to be better. Right? Okay. Let's go. More functions. If those are the only functions we have to deal with, that's fine, but there are more functions we need to use. That the first one, and we use quite often, is the inverse trig functions. Those are the ones. And we call this sine inverse? No, arc sine. And we use this arc for those functions. What it amounts to is that those are the ones we use from theta angle to sines and cosines. Okay. So, where this one is used? This one is used in the inverse kinematics. Joint angles from end effector position. So, you are given x and y's, and from that, you compute theta. So it's the other way around. That's why -1 is sitting here. That's why it is called arc sine, arc cosine, blah, blah. And one more thing is logarithmic function, log function. Once again, logarithmic, it's difficult to pronounce. So let's forget about this one, yeah? Log function. The two famous ones, ln x and log x. I'm going to talk about that in detail later. But anyway, when we have an equation of motion and solve that equation of motion to come up with trajectories, so to find the robot motion, we need that function. Okay, patchwork functions. This is my favorite function, by the way. Well, remember RoboKick? We have divided the time interval into 3 of them and came up with those, right? This is regularly used. I mean, we use this method so often, okay? So you divide the time interval into several different time intervals and you use different functions. This is very handy because most of the time you can use function which is fit to whatever the motion in that particular interval. Okay. So let's start talking about the polynomials first. Other functions later. Before starting polynomials, we have to talk about the power function here. This one here is a times a is, as I said, a constant. X is variable. To the nth power, n is an integer, right? This is index. So that's the type of function that we call that power function. If we put them together, we come up with polynomials. Put them together. So this is called the nth order polynomial. N comes from this highest power. Okay? Well, example we have used is the second order polynomial. This one here, we used it already. And one interesting example, extension here is the polynomial over polynomial. This type of function we use quite often when you're talking about the control theory of motors. we use this so often. But anyway, that's nothing but polynomial over polynomial. And those are called rational functions. By the way, do you remember rational numbers? Yeah, rational numbers can be expressed by integer over integer. It's the same idea here. Okay. Now, before going into the sinusoidal functions, etc., etc., let me just do a little bit of, how should I say, operations on the functions. And some of those typical operations are very useful. So let me talk about those. Like this one here, you add a number. And do you know what it does? This one does vertical shift. So if a is greater than 0, goes up, and less than 0 goes down. And if you multiply instead of adding, then that's vertical scaling. And if a is greater than 1, this enlarges. And if a is less than 1 but positive, then it shrinks. And if a is negative, it just flips vertically. And this one here, if you add, not that actually adding, if you subtract a number from the variable, what's going to happen is that it will shift horizontally. And if you multiply a number to the variable, then that's going to be horizontal scaling. So if you add or multiply to the function itself, that's vertical. If you subtract or multiply to the variable, that's horizontal shifting. Well, let's look at this function, ax squared, and see how it does. Okay, this is the original function, if x is equal to x squared. And I am going to add b here. I don't know why b. Could be a. Anyway, so what's going to happen? All right, here. If b is equal to 3, that's this one here. And then b is equal to 2, 1, negative 1, negative 2, negative 3. So, as you can see, adding b, you are shifting the function vertically. Well, how about this one here? You are subtracting, okay? This is subtracting a. What's going to happen? All right, value of a. If this is minus 3, goes to that way. And minus 2, minus 1, and 1, 2, 3. So altogether, it looks like this one here. So as you can see, this is a horizontal shift. Okay? The next one is vertical scaling. So we multiply, see here. So this is the original. Then, if c is equal to 2, it looks like that. And 1.5, 4.5. Yep, come on. Okay, this is negative 0.5, negative 1. Negative 2, so altogether, this is what's going to happen. Isn't that beautiful? So, it changes the scaling vertically. So, by combining them, you can do a thing like this one here. Well, which one is which? Well, I'll give you this as a homework, part of the homework. So, you will find that out. Okay. Trigonometric functions, trig functions. You know the definition of a trig function. Okay. You use a triangle, the right triangle, that's 90 degrees here. And the sines, cosines, and tangents are defined by the ratio of those numbers here. Okay. Sine theta is c over a, cosine is b over a, tangent is c over b. That's the definition. Nothing wrong with it. That's fine. But if theta becomes greater than 90 degrees, what's going to happen? Okay. It looks like this one here. Wow, this is not even a right triangle. So how do we define sines, cosines, and tangents? So instead of this definition of using triangles, we do have a definition using unit circle here. Unit circle, so the radius is equal to 1. Okay. This is theta 1, that's theta 2, that's theta 3. And this one here, you can use it for any angle. This theta 2 is greater than 90 degrees. Theta 3 is negative. But it doesn't matter. We can use that. And using this definition, originally that's a trig function, but sinusoidal function is another name we can use for that function. And that's where sines and cosines came from. Okay. Anyway, so sines theta I, theta 1, theta 2, theta 3 are, wow, y coordinate. That's it, y coordinate. And cosine is x coordinate, and tangent is just a ratio between these two. That's it. And 1, 2, 3 means I changes. So theta 1, y1, theta 2, y2, blah, blah, blah. Is what we're going to have. So this is easy. And it does not care where this theta 1 is, how big or negative or positive. So this is useful. Okay? And using this one here, what we can do is we can draw the functions for different theta. Here, this is sine theta starting from 0, y-axis, right? Y-coordinate starting from 0 goes to 1, goes to negative 1, etc. Cosine start from 1 because that's x coordinate, and goes to negative 1, comes up again. And tangent is the ratio between these two. So there is one point where cosine theta is equal to 0 here. It goes to infinity. Okay? So those are the graphs. Probably you have seen this already in the high school. And if you look at this definition, you can find many different nice, I call tools here. Namely, identities. Those identities are useful, and you can see those are true, but just take a look at the definition of unit circle here. Probably most interesting is this one here, the final one, sine square plus cosine square is equal to 1. Because whichever the one, let's take a look at this one here. This is a right triangle. So this square plus that square has to be this square. And that is equal to 1. Okay? Unit square, unit circle. So that square plus square is equal to 1 for any angle theta. Okay? And I'll give you a homework where you need to prove some of those. Okay, more interesting identity is this one here. This one is called the addition identity. Well, in Japan, every high school students who are interested in mathematics, engineering, blah, 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 they have to know this. You have to remember this one here. I hated to remember those, so I always prove this one here myself. How? There's an easy, very nice way. But in the high school, it is not easy. It's not simple at all. Okay? But at the university, you will learn very easy, nice way. Only 3 steps. That is the beauty of university mathematics. If you learn mathematics at the university level, you will learn to unify many different things you have learned in high school separately. So what you see is that there's unification. So if you do use one, you can show many different things. That's the beauty about the university mathematics. So this particular one we use Euler's formula. The most beautiful formula in mathematics. I love this formula. But for that, we have to learn exponential functions first. So let's look at the exponential function. That's fx is equal to e to the x. E is this number here, called the Napier's constant. Random number, right? No, really. This number is so special. Very special. What is so special about Napier's number? Well, let's consider a power function like this one. The difference is that here, e to the x power. Before, I gave you a similar function in polynomial where this x was an integer. But it is not integer anymore. This is real number here. Okay, this is a kind of function. And this is a fact. If you differentiate this one here, of course you're going to get some another different function here, right? But derivative of this one here is identical to the original. Identical to the original if a is equal to e. If a happens to be this number, Napier's constant, differentiating you get the original function. Differentiation doesn't do anything. Isn't that interesting? Differentiating doesn't do anything, meaning that the value of the function and the derivatives are the same. Speed and the function value is the same. That's so funny. I mean, strange, right? That happens only if this a is equal to e. Very special number. And there's no changes for my definition. And this is the only function has that property. That's why this function is so special. That's why this Napier's constant is so special. Okay. Well, the power function has lots of interesting and useful properties which we can use as tools. One of them is this invariant under differentiation. Differentiating, you get the original function. So it does not change. Wow. Okay. And e to the x power greater than 0 for all x. Okay. And e to the 0th power is equal to 1. That's true. For any number, 0th power is equal to 1. All right? So here, this is 1. And as x goes to minus infinity, goes to 0, and x goes to infinity, goes to infinity. Let's look at this one first here. Well, let's assume x is an integer. E to the second power is greater than e because e is 2.7. That's probably a little less than 10. 4th power, 10th power, 100th power, it gets bigger and bigger. So naturally, this one goes to infinity. And minus power, when x becomes negative, why this one goes to 0? Let's take a look at the next one. And next one. Okay, e to the minus x power is 1 over e to the x. Well, that's natural, right? So what's going to happen is that when x becomes very large, ex is very large, 1 over ex is very small. So therefore, this one goes to 0. But why is this true? Well, this is a key characteristics. Addition of exponent becomes the product. This is so handy. Actually, this one was used to find the logarithm table long time ago. Okay, let's go. Coffee break. Time for the coffee break. I love coffee. Complex numbers. Have you learned complex numbers in high school? Well, complex numbers, I love complex numbers. Given like this one here. Alpha plus j beta, where j is equal to negative 1. Square root of negative 1. And you say, wait a minute. We didn't learn that one. You must have learned that square root of minus 1 is equal to I. Probably that's what you have learned. But in university, in the field of robotics and engineering, especially electrical engineering, we do not use I for root of -1. Why? Because I here is reserved for current, electric current. So we cannot use I for this one. That's why we use J here. And this alpha and beta are called the real and complex parts. And real part alpha and complex part beta are real numbers. Well, what's so special about that? Well, nothing special, but those are real numbers. If they are complex numbers, it messes up everything, right? So, and because of that, two complex numbers are equal if real numbers are equal to each other and complex numbers are equal to each other. I'm going to use this one here in proving the next thing. As you already know, complex numbers are complete. Do you know? Probably you don't even know whether you know it. You know it. Like, second order polynomial is equal to 0. You try to find the roots for this equation here. And you know that sometimes roots becomes complex, right? And if you're talking about the real numbers only, then sometimes, depending on A, B, and C, you cannot find root. But if you include the complex numbers, you can always find the roots. That's the completeness. One good example of the completeness. Okay, coffee break 3. This is exactly this is actually what I wanted to talk about. Euler's formula, the greatest treasure of my life. Wow. I strongly believe that. What is it? Well, we first look at a function, which is a strange function, exponential function, yes, with imaginary exponent. So we have j here. It's the jx. What is this? What is this? We don't even know, right? But Euler said that e to the jx is equal to cosine x plus j sine x. I can prove that, but probably next year I'll prove this one. So this is astounding, really big surprise. Well, suppose x is equal to pi. Okay, if you put the pi in it, e to the j pi is equal to cosine pi is -1 and sine pi is 0. So this is it. So what's going to happen is that the e to the j pi and added 1 becomes 0. E is 2.7 something something, a Napier's number, quite a number. Pi is 3.14 blah blah blah, again quite a number. J, square root of -1, and combine everything together and add 1, everything vanishes. Well, I feel that's very beautiful. But anyway, so why this is useful? Why this is the greatest treasure? Well, one small demonstration of that is addition law. Okay, if the jx plus y is cosine x plus y, j sine x plus y, just using this one here, and also that can be broken down into the product. And if you use one more time, we have this, and what? We just multiply them out. Cosine times cosine minus j squared, so that's minus. Sine times sine. And cosine times sine j, and sine times cosine j. So, this is the result. And this is the real part, and this is the real part. Okay? And also, this is the imaginary part, and this is the imaginary part. So, those two numbers are equal to each other, meaning that this is equal to that, and this is equal to that. Aha. Those are the two formulas of the addition law. So I use only 3 lines. and proof was so simple if we use Euler's formula. That's the beauty about Euler's formula. Okay. Well, I have talked about a lot of formulas and so forth, and I'm sure you cannot remember them. So I put together all those formulas into a formula sheet. Well, this is not good English, right? A formula sheet is available. Well, let me tell you, originally there were more than one sheet, but I crunched into one sheet. And polynomial, trig, and exponential, log, blah, 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 are in it. And that is available on the web, so I'll give that to you. Thank you.